In this video I'd like to take a look at another very useful operation that we can apply to a 2D Cartesian vector, and that's the operation of finding the magnitude of that vector. Now the magnitude of a vector is just a fancy way of saying we're finding the length of that vector. So if I had a vector v, if this was a 2D Cartesian vector, we know we'd have an x component and a y component. We'd also know that we can graphically represent this vector in our 2D Cartesian space. So if we had a 2D Cartesian space, we can graphically represent this vector as a directed line segment. So we're trying to find the magnitude of this vector. We're trying to find the length of this vector. So what we're really doing is we're trying to find the length of this line segment. In other words, we're saying if we start at a particular point in our Cartesian space and we travel down the length of our vector, how far have we traveled by the time we reach the end of our vector? Once again, this is called the magnitude of our vector. The magnitude of our vector. And there's actually a mathematical notation that we can use when we're saying we're finding the length or the magnitude of a vector. So if this is our vector v, and we're saying we're finding the magnitude of v, the mathematical notation that we use is a double vertical line before v and a double vertical line after v. So this is the mathematical notation to say we're finding the magnitude of v. We're finding the magnitude of whatever is between these pairs of double vertical lines. So we're trying to find the length of this vector v. Well, how are we going to do it? Well, actually, this is very similar to a problem we saw back in Volume 1, where we tried to find the distance between 2 points in 2D Cartesian space. If you recall back to Volume 1, if we had 2 points in 2D Cartesian space, the way we found the distance between those points was to construct a line that goes between those 2 points. And we said if we had a line between those 2 points, the distance between those points is equal to the length of that line. But how do we find the length of that line? Well, in order to do that, we constructed a right-angled triangle such that one edge runs parallel to the x-axis, the other edge runs parallel to the y-axis, and this line is the hypotenuse of that triangle. Now, using the coordinates of the 2 points, we were able to find the length of the 2 edges that run parallel to x and y, and with the length of those 2 edges, if this was a and this was b, and let's say the length of the third edge, the hypotenuse here is c, with the length of these 2 edges, we're able to use Pythagoras' theorem to find the length of our hypotenuse, and that theorem once again is a squared plus b squared is equal to c squared. For those of you who maybe aren't familiar with it or needed a bit of a refresher, that is Pythagoras' theorem. And we use Pythagoras' theorem to find the length of our hypotenuse, which of course we said the length of this edge is the distance between our 2 points. So that's how we found the distance between 2 points in 2D Cartesian space. But how are we going to find the length of our vector? Well, what if we considered the same problem? What if we thought of our vector, our directed line segment, as being this hypotenuse? What we need to do is we need to construct an edge that runs parallel to x and an edge that runs parallel to y. So we could do that. We could construct a right-angled triangle with an edge that runs parallel to x and an edge that runs parallel to y. Now, in order to find the length of our hypotenuse, which is the length of our line segment, which is the magnitude of our vector v, in order to do that, we need to know the length of this edge a and the length of this edge b. So let me just erase this guy for a second, and also delete out that shape that we drew because we don't need him anymore. Fantastic. So we know that a squared plus b squared is equal to our hypotenuse squared, and we know our hypotenuse is the magnitude of our vector v. So a squared plus b squared is equal to the magnitude of our vector v squared. So in order to find the magnitude of our vector v, we need to find the length of a and b. Well, what about the length of a and what about the length of b? How can we find these? Well, it's actually very, very simple. If we think back to how we defined our vector and how we get our graphical representation of the vector, we need to think back to our Cartesian components. And we know, using these components, that they tell us that our vector travels a certain distance in x and a certain distance in y. So from the start point of our vector, wherever that is, because of course our vector is free to float around Cartesian space, from the start point of our vector we travel a certain distance in x, and that distance is given by our x component, and then we're travelling a certain distance in y, and that distance is given by our y component. So again, we travel a certain distance in x, which is given by our x component. So that's the same as saying this edge here is equal to our x component in length, and then we travel a certain distance in y, and that's given by our y component. So that's the same as saying that this edge here is equal to our y component in terms of length. Now you'll notice this has no restrictions based on the position of our vector, no matter where our vector is positioned in Cartesian space, because it's not locked to a specific position, it's free to float. We're always travelling a certain distance in x and a certain distance in y. We're always travelling that distance because that's how this vector is defined. It's the very definition of this vector. So we're always going to have this right angled triangle as defined by our components. So we said that a, the length of that edge, which we said was a, is actually x, so x squared, and b, the length of the vertical edge, is actually y. So what we've got is that x squared plus y squared is equal to the length of our vector squared. And this is very obvious now that we've got this right-angled triangle, because it comes from Pythagoras' theorem. We're simply saying that if we travel a certain distance in x and a certain distance in y, we can construct a right-angled triangle to represent that, and we can find the length of our hypotenuse by using Pythagoras' theorem. So if this x squared plus y squared is equal to the length of our vector squared, the magnitude of our vector squared, then we can clearly see that the magnitude of our vector is equal to the square root of x squared plus y squared. We take the square root of both sides, it's going to give us the magnitude of our vectors equal to the square root of x squared plus y squared. And because we're finding the length of our vector, we're worrying only with the positive value that can be returned from our square root. We don't need the negative value, because again, we're finding a length. That means our magnitude is going to be a positive value. So the magnitude of any 2D Cartesian vector v, given by the components x and y, is equal to x squared plus y squared. So we can use this to find the length of some example vectors. So if I had a vector A that is equal to, I don't know, 2 units in x and 1 unit in y, and I wanted to find the length of this vector A, how do I do that? Well, I need to use this very simple equation right here, which says the length of A is going to be equal to the square root of x squared plus y squared, which means it's going to be equal to the square root of 2 squared plus 1 squared, which is equal to the square root of 4 plus 1, which is equal to the square root of 5. Now this isn't a nice round number, so I'm not going to worry about actually finding the value of the square root of 5. I'm simply going to leave this as the length of A, the magnitude of A, is equal to the square root of 5. So there's one example. Let's take a look at another example really quickly, though I imagine everyone by this point has already got how we do this, because it's a very, very simple operation. So let's say this is 8 and this is 6. That means the magnitude of B is equal to the square root of x squared plus y squared, which is equal to the square root of 8 squared plus 6 squared, which is equal to the square root of 64 plus 36, which is equal to the square root of 100, which in actually this case is a nice round value of 10. So the magnitude of B in this case is equal to 10. Well, why is the magnitude useful to us? Well, there's multiple different reasons really why the magnitude is useful to us. The first reason that comes to mind takes us back to when we first introduced the idea of vectors. And we introduced the idea of vectors by talking about velocity. We spoke about velocity, and we spoke about it containing the speed that someone was travelling along with the direction of travel. And we went through a number of stages until we came to our Cartesian representation of vectors. Well, we said we could represent our velocity as how fast are we travelling in x and how fast are we travelling in y. But what if someone gave me this velocity vector and they said, my velocity is equal to, I don't know, 10 miles an hour in x and 5 miles an hour in y. But I wanted to actually know, what is my speed? What is the speed that I'm doing, irregardless of the direction and irregardless of how fast I'm going in x or how fast I'm going in y? What is the speed that I'm travelling at? Well, what I'm interested in that case, if I drew a very small diagram here, what I'm interested in is this is our velocity vector, which is 10 units and 5, so something like this. And we're saying we're travelling 10 miles an hour in the direction of x and 5 miles an hour in the direction of y. What I'm interested in is how long is this vector? In other words, the magnitude of this vector, because that's going to tell me the speed that I'm travelling in the direction of our vector. That's what our vector represents. So if we had a velocity and we wanted to find the speed, we simply calculate the magnitude of our velocity. That's equal to 10 squared plus 5 squared, and we take the square root of that, which is equal to the square root of 100 plus 25, which is equal to the square root of 125. I'm not going to simplify that down any further. We could use a calculator. We could simplify this down for those of you who are familiar with working with square roots, but I'm not going to worry about that here. So we've got the magnitude of v, and that's going to tell us the speed that we are travelling in, regardless of the direction of travel. Although we know the direction of travel is given by this vector, that's the speed, the true speed that we're travelling. So it's not how fast are we travelling in x, it's not how fast are we travelling in y, it's how fast are we travelling. So it can be very useful for finding the speed when we know the velocity as a vector. It can be useful for other purposes. We've already discussed finding the length, the distance rather, between 2 points in 2D space. Well, we could actually construct a vector that travels between 2 points in space and then use the magnitude of a vector to find the length of the distance rather between those 2 points. I mean, it's a little bit redundant because we've got our equation from volume 1, but let's look at it here because it's actually quite useful to see how we can construct a vector between 2 points as well as then use that to find the distance between those 2 points. So I'm going to bring up a new whiteboard really quick. There we go. So if I had 2D Cartesian space with an x-axis and a y-axis, and I had 2 points in that space, and let's say this point was 2 in x, 2 in y, and this point was 8 in x and 6 in y, say, and I want to find the distance between those points. Well, we had our formula from volume 1. I'm not going to get into that here, though you're going to see very quickly how that formula directly relates. If you are familiar with that formula, you're going to see how quickly it directly relates to what we're doing here with the vector. But what I want to do is I want to construct a vector that has the direction that goes between these 2 points, as well as having the length of the distance between those 2 points. Now, of course, the important thing to remember here is that vector is free to float around our Cartesian space. It's not specifically locked at the point that we're using as the start point. However, if we did start the vector at that start point, it would end at the second point, which means if we find the length of the vector, we find the distance between these 2 points. Now, why is it useful to be able to construct a vector between 2 points in Cartesian space? Well, at the moment, we're just finding the distance between those points, and we've got another equation that we could use to do that. But later on, we're going to see many different, very useful operations that we can apply to vectors that we can't just do with the coordinates of the points. So by being able to construct a vector between points in Cartesian space, we can apply these various operations of vectors to solve problems that relate to those points. And we're actually going to see that much later on in this DVD, where we use the 3 vertices of a triangle in 3D Cartesian space to construct some vectors on that triangle and use those vectors to find the surface normal of that triangle. Now I'm getting ahead of myself by introducing that here, but I just wanted to point out that it all comes back to being able to find a vector between 2 points, in this case in 2D Cartesian space. Later on we'll see how we can do it in 3D Cartesian space, and it's a very, very simple operation really. It's a very simple method. So what we're trying to do is we're trying to find a vector. We can call this vector v, which means we're trying to find how far are we travelling in x and how far are we travelling in y. So all we're really doing, once again, is we're breaking this down into a movement in x and a movement in y, which gives us this right angled triangle, much like when we're trying to find the distance between those 2 points. How do we find the movement in x? We need to see where we started in x, where we finished in x, and find the difference between them. We can see if we started at 2 and we finished at 8, we have travelled 6 units in 8. So 6 units in x rather. So we take the second point, the end point, and we subtract from it the start point. So we take 8 minus 2, and that gives us 6. We've travelled 6 units in x. Again, the important thing here is we take the end point and we subtract from it the start point. We can also do this in y, so we take the end point, that gives us 6, and subtract from it the start point, that gives us 2, which means 6 minus 2 is 4. So the components of our vector are 6 in x and 4 in y. We could then find the magnitude of our vector, which will give us the length of our vector, which will give us the distance between these 2 points, which is equal to the square root of x squared plus y squared, so 6 squared plus 4 squared, which is equal to the square root of, I scroll down to give myself some room, 36 plus 16, which is equal to the square root of, that's going to be 4652, which again, that's not a nice round number, so I'm just going to leave that written as the square root of 52. So the distance between those 2 points is the square root of 52. But more useful than being able to find the distance is the fact that we've constructed a vector between these points. Now we're going to see a more mathematically rigorous way of doing this a little bit later, but for now all we really need to know is the fact that we've taken the end point, we've subtracted from that the start point. That's told us how far have we travelled in x, how far have we travelled in y. That gives us the components of our vector, and then we've used that to find the distance between those points. And hopefully for those of you who did follow along with volume 1, this is kind of showing a nice parallel, if you will, to what we did in volume 1 to find the distance between the 2 points, because you can see we've actually done the exact same thing. We've taken the coordinates of one point, subtracted the coordinates of the other point from it, squared those results, added them together, and then calculated the square root. The only difference is that here we've converted those 2 points into a vector, and that vector does have a set direction where we take the end point and subtract from it the start point. Once again, that is important. It's the end point minus the start point. If we'd done this in the other order, if we'd taken the start point and subtracted the end point, you'll notice we'd have got a vector that runs between those points, but it would have run in the opposite direction. So I did get a little bit sidetracked there, but I thought it was kind of cool to show this, just so that those of you who'd seen the methods that we used in volume 1 to find the distance between 2 points could then see how that relates to finding the length of a vector very explicitly when we're using numbers here. So getting back on track, we've seen how we can find the magnitude of a vector, and we've seen that very simply, if we have a vector given by x and y, we can find the magnitude of that vector, which is equal to the length of that vector, as the square root of x squared plus y squared. So all I'd like to do now is just set a couple of questions. It's going to be very simple questions. There's nothing to what we've covered in this video right here. But I do want to set some questions just so you have some practice working through this on your own. So question 1 is going to say we have a vector. I'm going to say our vector is A, and it's going to be 3 in x and 4 in y, and what I'd like you to do is tell me the magnitude of vector A. So go ahead and pause the video, and when we come back I'm going to work through the solution very quickly here on the whiteboard. Okay, welcome back everyone. So this shouldn't take us very long at all, because we know the magnitude of A is equal to the square root of x squared plus y squared, which is equal to the square root of 3 squared plus 4 squared. That's going to be equal to the square root of 9 plus 16, which is equal to the square root of 25, which we know is equal to 5. Again, we only take the positive value because we're dealing with a length. We're dealing with the length of the vector. That's going to be a positive value, which gives us the answer of 5. So hopefully you wouldn't have had any problems plugging these numbers into the equation. If you did, just make sure, of course, firstly, that you were using the correct equation. The magnitude of our vector is equal to the square root of the x component squared plus the y component squared. Then just make sure you fully understand what these mean and how they relate. If you don't, then watch over this video again and hopefully you'll pick it up. This is our vector with its two components. This is the length of our vector and how it relates to those two components. But hopefully everyone is very comfortable with that. It's quite a simple concept, and hopefully you got the correct answer here for this question. So I'm going to set one last question. And this question isn't going to have a nice round answer, so you can leave it in its square root form. And this is going to say we have a vector b, and that's going to be equal to 5 and 7, let's say. And I'd like you to find the magnitude of b. So go ahead and pause the video, give this an attempt on your own. When we come back, I will work through the solution here on the whiteboard. Okay, welcome back everyone. So the magnitude of b, we know, is given by the square root of x squared plus y squared, which in the case of b is the square root of 5 squared plus 7 squared, which is the square root of 25 plus 49, which is equal to 25 plus 40 is 65, plus 9 is 74. So it's equal to the square root of 74. Fantastic. So I'm not going to simplify that down. I'm not going to use a calculator to get this answer. I'm simply going to leave it here in square root form. But that is the answer for the length of our vector with an x component of 5 and a y component of 7. So once again, to recap the most important points of this video, because we did go on a little bit of a tangent where we were finding the distance between 2 points. So I did want to show that just so you'd seen it. But the main focus of this video is that if we have a vector in 2D Cartesian space given by an x component and a y component, the length of that vector, the magnitude of that vector, is given by the square root of the x component squared plus the y component squared, and the notation for that is our vector surrounded by a pair of double vertical lines. And with that, that is going to conclude this video. Thanks a lot for watching, everyone.